morning and welcome to lecture 4 of our course on particle characterization. In the last lecture, we started talking about shape assessment techniques, and we kind of went through the history of how particle shapes have been measured, and we also discussed various categories of particle shape assessment, and we classified particle shape analysis methods into methods based on single particle analysis, methods based on analyzing properties of bulk powders, mathematical techniques, and verbal descriptors. So, these were the major classifications of particle shape assessment methods. I also said that in each of these classes you can further categorize the methods. For example, single particle analysis methods can be further classified into methods that are based on measuring the distances between tangents that are parallel to the contour of the particle, methods that are based on shape comparators, and methods that are based on measuring the lengths of specific types of intercepts. So, in this lecture we will first begin by discussing these three methods in a little more detail. Okay. So, again the first method is distance between tangents that are parallel to the particle profile. The second is shape comparators. And the third method is lengths of intercepts. In a way, these were the earliest methods used for shape analysis, and the reason for that is because in the old days the equipment that was available to us for doing this characterization was fairly crude. You could not achieve very high magnifications, or if you could, it was very expensive. So, people had to do with limited resources, both in terms of analytical equipment as well as to some extent the expertise of the people that were using this equipment. So, what they tried to do was minimize the number of data points that they took on each particle in order to do its shape characterization. Many of these techniques are essentially geometric techniques. So, they try to reduce a 3-dimensional object like a particle to a 2-dimensional profile, and then do their shape assessment based on this projected 2D profile of the 3D object. Certainly limited in its scope, limited in its effectiveness, but it was the right thing to do at the time. So, if you look at some of these methods today, they may look very unsophisticated, but at the time when people started using these methods, they represented the state of the art, so to speak. So, the first method, distance between tangents, the guy that really innovated this was a person by the name of Hayward, who took the profile of the particle and he measured the distance between parallel planes in one arbitrary direction, and he called it L. So, the selection of this L dimension was entirely arbitrary. Then what he did was took a plane that was perpendicular to this plane, and again measured the distance between tangents that were parallel to the contour in this perpendicular plane, and he called that B. And then he took a third plane which was perpendicular to both the first and second, and again he drew tangents to the profile of the particle in this plane and measured the distance between the tangents, and he called that T. So this L, B and T obviously represent length, breadth and thickness. However, Hayward really made no effort to classify them as such. I mean, he did not say, for whatever reason, that the longest dimension should be called L, the shortest dimension should be called T, and the intermediate dimension should be called B. The advantage of the Hayward methodology is the simplicity. It did not require a quantitative comparison between the 3 dimensions that he was measuring, but for every particle it yielded 3 dimensions which could be used as a shape representation. Now, after this, there was a person by the name of Krumbine, who took this analysis one logical step further, and he said the longest dimension that is measured in this fashion should be called length, L prime, and he said the shortest dimension should be called thickness, or T prime, and then the intermediate dimension will be called breadth. So almost a trivial extension of what Hayward had done. After this, the third person that really got involved in shape analysis was a scientist by the name of Lee, who made this approach more systematic and in a way more convoluted from an analysis viewpoint. He also said that we should start with the longest dimension and label it as L, but then what he said was that we should take the longest dimension in the cross section of the particle and call that B, and he said take the longest dimension in the narrowest plane of the particle and call that T. Now, the key difference though between Lee and Krumbine in particular was that Lee said these dimensions do not have to be orthogonal to each other, they do not have to be perpendicular to each other. So, L, T and B could essentially be chosen as any 3 axes that represent the diameter of the particle in the various planes, and as long as they represent the longest dimension requirements in these various planes, they could be taken as L, B and T. Now, with this definition, it became easier for different groups of researchers to look at the same particle and characterize it using by the same dimensions. The problem with the Hayward approach is that even though it may have worked very well for his own research group, it was very difficult to share the results across labs and get convergence from various groups on what the actual dimensions of the particle were. So this approach by Krumbine and later by Lee certainly made it a lot more systematic. So this was really the first effort at shape characterization by identifying 3 critical dimensions of the object. This led to then the second method of shape analysis, which is shape comparators. Now that you have measured L, B and T, you can always take, for example, the ratio of B over T, and you would call that, what would that represent? It was called flatness ratio. And similarly, L over B was called elongation ratio. So what do these ratios represent? Why do we take ratios? It's the same reason why as chemical engineers we try to non-dimensionalize everything, right? The reason is to be able to compare across systems. So if you have two particles and you want to compare the flatness of these particles, then this ratio gives you a non-dimensional value that you can use to do this comparison. So such ratios that are derived based upon your fundamental measurements are called shape comparators. So these were actually defined by Hayward. Now there was another person by the name of Waddell who defined his own shape comparators. He did that by first defining something called F, which is a surface shape coefficient, and K is a volume shape coefficient, where F is derived by essentially taking F times d squared equals P, where AP is the projected area of the particle and dP is the projected area diameter. So the way you calculate F is simply by AP over dP squared, and similarly K was defined by Waddell as the volume of the particle divided by dP cubed. He then proposed shape comparators that were based upon these values of F and K. For example, he defined sphericity, which is obviously a measure of how spherical the particle is, and his definition was sphericity equals 4.84 times K to the power 2 by 3 over F, which is a non-dimensional value, by the way. So here again what he is doing is similar to what Hayward did. He takes certain measurements of the particle, whether it's length, area or volume, and then develops non-dimensional ratios that enable us to compare shapes of different objects. Another shape comparator that Waddell came up with was roundness. The way he defined roundness of an object, of a particle, was essentially by taking the profile of the object in a two-dimensional plane, inscribe a circle inside it which gives a best fit. So from here you take the diameter of this inscribed circle which gives the best fit to the profile, and then so that actually goes in the numerator. Let's call this some DC. He then divided that by the mean diameter of all the curvatures that are present in the particle. So essentially he would draw radii towards all the peripheral points of the object, take the average of the actual radii or diameter that linked the profile of the object to its center, and he would then average it and obtain a mean diameter that represents the actual profile of the object. So, the idea is that if you have a more rounded particle, this ratio would tend to 1 because dc will be equal to every d value, whereas the farther the deviation from roundness of the object, the greater will be the deviation of this ratio from 1, because it could be greater than 1 or lesser than 1 depending on the shape of the object. A similar shape definition that he came up with was called rugosity. Rugosity is a measure of surface roughness, how rough the surface is. So, the way that this definition works is in some ways similar. So, you take an object which may be very rough, particularly in a 3-dimensional scale around the periphery, and you fit it with a smooth profile, and you take the perimeter of the smoothened profile of the object and divide it by the actual prevailing perimeter of the particle. Now, when we say prevailing perimeter, you actually have to look at all the roughness elements that are present on the surface, and you have to take the total length. So, you have to move along the roughness profile and measure the actual perimeter of the object using that technique. And again, this ratio gives you a quantitative indicator of how rough the surface is. The rougher the surface, the smaller will be this value, because the effective perimeter of a rough object can be many times the perimeter of a smooth object with the same radius, for example. So, all these definitions of flatness ratio, elongation ratio, sphericity, roundness, rugosity are all examples of that second class of shape analysis methods, that is shape comparators. So, let us look at a few more examples of how these shape comparators work. So, we go back to Hayward. He also defined certain shape values. The way he did it was, again, by taking the particle projection in 2 dimensions, he would then inscribe it in a rectangle which completely encapsulated the object. So, it will be the rectangle with the smallest dimensions that could completely encompass the object, and he would call the longer dimension here as L and the shorter dimension as B, and he would then define an elongation ratio for the particle as simply L over B. Now, the other thing that he also defined was a bulkiness index, how bulky is the object, and this he did by essentially taking the area of the object in 2 dimensions, the projected area, and dividing it by A times B. So, the larger this ratio, the bulkier the object essentially. Yeah. Oh, sorry, L times B. So, again, these are examples of shape comparators which can be very conveniently used by research groups working across several labs to come up with the same description of a particle. Now other people have actually taken some of these analysis and extended it to more classes of particles. In the early days, much of the work was obviously done with fairly large objects. So particles were millimeters to microns in size, and so shape characterization was a very different challenge in those days compared to today, when many people are dealing with nanoparticles. So the extension of some of these techniques to nanoparticles and submicron particles is something that particle scientists are still going through, because some of these methods do not really lend themselves to use as you start approaching the nano dimensions. And as the particle dimensions shrink, it becomes more and more logical to use mathematical techniques, digitization, and so on. But these methods have their own attractiveness. They are very simple to use and very intuitive. I mean, a definition of something like this for bulkiness you can intuitively understand. If you ask a computer to come up with a measure of how bulky it is, it will probably take a long time to do it, and then it will give you a number which you probably won't even understand physically what it means. So there are certain inherent advantages in the way that we used to do shape analysis, even though they were very cumbersome, time consuming, and sometimes hard to reconcile between various researchers, but they did have the advantage of really capturing the essence of the shape of the object. Okay, so let's talk about the third type of method, which is the length of intercepts. We briefly looked at an example of this in the last lecture. There was a person by the name of actually I guess the first one was Church, who developed the technique that I outlined in the last lecture. So you take an object or a particle and take a microscope and you orient the particle at some angle theta, and then you measure two intercepts, right? The shorter intercept with the y axis is called the Martin's diameter, and the longer intercept with the same axis is called the Ferret's diameter, df. And Church basically said that a shape coefficient could be defined as a ratio of dm over df. So here again, as it's really a measure of elongation more than anything else, and this method was most popular for the use of elongated particles. The closer this ratio is to 1, the more spherical the particle is, and the more elongated the particle is, the greater will be the difference between dm and df. So the ratio will be much smaller. So for a highly elongated particle, this ratio will start approaching 0 basically. So the way that Church did it was to do this analysis for a few random values of theta, and then average the data and statistically analyze the data to come up with a metric for the shape of the particle. A person by the name of Cole took this idea and just made it more systematic. So he said, why don't we do a proper image analysis study using a computer and image capture visualization systems, and look at as many values of this this ratio, which is a function of this value theta. So let's increase the number of theta values to as large a number as possible until we have a converging value for this ratio. So the Cole technique was to plot theta versus dm by df and essentially reach a converging value after a certain number of theta values. So, essentially the image analysis and the calculation of the Martins and Ferret's diameter will continue until you reach a limit, which could happen either this way or this way of course, but essentially what you look for is a value of this ratio which is invariant with changing theta, because at that stage you have essentially converged to a definition of these diameters which you know will not change just by taking more observations, so to speak. So, these two methods are very similar, very closely related to each other, and they are based upon intersections of the two dimensional profile of the object with the vertical axis in your eyepiece in a microscope, for example. The third method under this category of lengths of intercepts was contributed by a person called Chalkley, and he is the one that proposed the needle throwing method that I again briefly described in one of the earlier lectures. He said if you have an object and I want to know essentially either the ratio of the diameter to the perimeter or area to volume of this particle, then a way I can do it is to take needles of some known length L and throw it with a known force across this profile, and let us say that C represents number of times the needle cuts the profile, and H represents the number of times both ends of the needle are embedded within the profile. And then he said if you just take L multiplied by H and divide by C, this will give you the essentially again the way that the quantity of material is packed within this particle, which is what we call shape. So, the idea is that if you take the length of the needle and you multiply it by the number of times they are both embedded within the profile, that tells you that the profile is very long essentially, because the more elongated the profile of the object, the more likely that the needle will become completely encapsulated. So, if you take LH by C, that should give you an idea of volume per area of the particle, the projected volume to the projected area of the particle. Basically it would say that for a given area, if a needle is likely to get embedded in the profile, it is likely to have more volume, which is essentially an indicator of how bulky it is, right. So, LH by C you can look at as an indicator of again how bulky the shape is, and similarly you can also look at perimeter over diameter, and very roughly speaking there should be good correlation between these two values with probably some constant multiplication factors, but this ratio of LH by C should be a reasonably good representation of both the volume per unit surface area of the particle as well as the perimeter per diameter of the particle. So, these are some interesting attempts to characterize particle shape in a very intuitive way, right. instead of resorting to highly sophisticated visualization or measurement or mathematical techniques, but these were still designed to probe individual particles. Now, the other class of analysis methods that I had mentioned earlier were those based on bulk properties of powders, which simplifies the problem even further. So we'll discuss that briefly. So when we talk about analysis of bulk powders to extract shape, what we are trying to do is actually look at predominantly transport and storage characteristics of these powders, and from that obtain information about shape distribution within these powders. So one of the key parameters is the settling characteristics of a powder. Settling not in the sense of a particle settling in a fluid, but rather settling during storage, which is represented in the density. Essentially, if a powder is stacked in a very loose fashion, the bulk density would be very high, would be very low, because there will be less mass occupying more volume. As you compact it further and further, the density will keep increasing, right? So supposing you take a loosely packed powder and measure its bulk density, and then you did something to this powder to make it settle and become more compact, and then you measure the density again, the ratio of the bulk density in the free powder form versus the density in its packed form is actually an indicator of shape distribution within the powder. So there was a person by the name of J.K. Beddoe who came up with a test that's called the Rotab test, where he took this concept and made it into a systematic procedure. So this the Beddoe test essentially specifies how the powder is prepared for testing, it specifies how the bulk density is measured, it specifies how the powder is made to settle, and in this case it's basically done by using a hammer in a rotational setting to repeatedly tap on the container in which the powder is stored. So as you tap on it more and more, it settles and essentially reaches an ultimate bulk density value for a highly densified powder. So you take the ratio of your initial density rho I to the value of the tap density, and he defined this as a shape coefficient for the entire powder. So what is the relationship between the ratio of initial to tap density and the shape distribution in the powder? Well, when you think about it, if you have a powder containing very regularly shaped and very uniformly shaped particles versus a powder that contains highly irregular and highly non-uniform shaped particles, their settling characteristics will be very different, right? You would expect that if you have a powder that's formulated with all smooth spherical particles and you tap it, what's going to happen to it? It's going to settle into a highly compact, almost sintered type of a powder. It's going to have very high density because the surfaces are going to be very conformal. On the other hand, if you have a powder in which the particles of varying shapes ranging from highly spherical to highly elliptical, and if you have a highly non-uniform distribution of shapes in the powder, the settling is not going to happen easily, because if you have two particles side by side and one is spherical in nature and the other is needle like, actually the surface area of contact between the particles is minimal, and that alone, as we will see later, prevents cohesive behavior. And so by simply doing this tap test, you can actually fairly clearly identify whether a powder has predominantly spherical particles or predominantly non-spherical particles. The other way that you can characterize shape distribution is by looking at flowability. Here again, what you are taking advantage of is the fact that a highly cohesive powder will flow like a slug or a solid, whereas a powder that is not cohesive, where the particles remain as individual entities, will continue to flow like a Newtonian fluid. So by looking at essentially the flow characteristics and characterizing how Newtonian or non-Newtonian it is, you can actually get a good idea of how cohesive the powder is, and from the cohesion characteristic you can actually extract the shape distribution. Again, the basic thought process is the more similar the particles are and the closer to sphericity they are, the more cohesive they will be during their flow process. So this will give you kind of a macroscopic estimate of the shape distribution of particles within the powder. And the other characteristic that you can look at would be the porosity of the powder under different compaction stresses, which again is really a measure of how closely do the particles want to mate to each other, how much interfacial space they are going to leave when you compact them. So here again the primary consideration would be how much does porosity change as you compact the powder. If the powder porosity is greatly reduced when you do compaction, again it's an indication of highly uniform and nearly spherical particles in the population, whereas if the porosity does not really respond to compaction, that would be an indicator that you have particles that really are highly dissimilar and highly irregular. Okay? So these are functional methods of testing shape. I mean, if you are using these particles in a powder form in a process industry and you primarily care about how they flow, then what is the use of doing the single particle analysis that we had described earlier? All you really care about is when I make this powder flow, how is it going to flow? Am I going to see Newtonian flow or am I going to see non-Newtonian flow? So again, goes back to the point I made in my first lecture, that particle characterization is very tricky business, and you want to simplify it as much as possible. If you can get away with just doing bulk property characterization of powders, fine, go ahead and do it. Don't even bother with characterizing at single particle level. Okay, any questions on these two techniques? So far we have talked about single particle analysis and bulk powder property analysis. The third class of shape analysis methods that we discussed was mathematical techniques. Now if single particle analysis kind of is in the middle, bulk property analysis represents one end of the spectrum where you are really minimizing the amount of information you collect on an individual particle basis. Mathematical methods represent the other end of the spectrum where you are maximizing the amount of information that you extract about individual particle shapes. Now the way that mathematical analysis works is the first step is always you have to capture the particle, you have to capture its image, and you have to digitize its profile. That is where it starts. So essentially capture the three-dimensional image of the object and use software to discretize or digitize its outer profile. So what you now have are a collection of x, y, z points in space, right? Now what do you do with that? Well, the easiest thing is to essentially leave it as is, leave the information as digitized information, and then if you want to recreate the image of the particle later on, simply feed in the same x, y, z points and the computer should be able to recreate your object. And remember the Hausner requirement I mentioned earlier, that the objective of shape analysis is that the user should be able to reproduce the shape of the object. So, with simple digitization of the profile, you can in principle completely reproduce the external contours of the object. Of course, the more sophisticated your digitization algorithm, the more data points you take, the more precise is going to be your reproduction of the profile of the particle. But the other thing you could do is, instead of just stopping with the discretization, you can fit a polymer and actually try to get a continuous representation of the surface instead of a discontinuous representation. So, polymer fitting and representing the surface of the particle in a polymeric form is certainly possible, but there are certain risks associated with that. In fact, there is a finding that the closer the fit of the polymer to the points that you have taken, the greater can be the deviation from the actual profile of the particle. In other words, if you are using certain mathematical algorithms to get the best fit of a polymer to the digitized points that you have obtained, you can actually start deviating further and further from the actual profile by trying to do this curve fit or data fit. So, there is a risk associated with using polymer fits. The more you try to improve the fit, the more error you may be introducing in terms of the deviation of the shape that is recreated from the shape of the object. The third method is to use Fourier analysis. Now, Fourier spectra essentially are unique to every particle shape, just like Fourier spectra of organic materials are unique to every material. So, using a Fourier analysis, you should be able to capture the key features of the profile of the particle, and at that stage you can either use this once again to recreate the particle at a later time, or you can store it in a database or in a library and compare it with shapes that have been generated, let us say by other researchers or by your own lab, where you have built up a database of known shapes and their associated Fourier shape spectra, and then you can compare the Fourier spectra for your particle against the ones that are in the library, and by doing this comparison you can see where the best fit is and represent the shape of your particle by the corresponding best fit shape in your library. So, the Fourier analysis technique does enable you to take your shape analysis one step further and actually start building up a reference spectra library that you can use in future and which other groups of researchers can use as well. So, the mathematical techniques represent the most sophisticated method for shape analysis, and it is certainly very widely used now because of the computing power that is available, but you always have to be careful that in many cases it may be an overkill. If you are not a particle scientist working in the area of shape characterization, most likely it is too much. If you are a process engineer working in industry, the absolute recreation of the precise shape, three-dimensional shape of a particle may not really be required in most cases. So, do think and customize your method of shape analysis. You have three techniques to choose from so far: single particle analysis, bulk properties of powders, and then mathematical analysis of the profile. And again, these represent the one end of the spectrum, the middle of the spectrum, and the other end of the spectrum. So, clearly you have to make the choice as to where you want to be, or do you want to be in the middle or at one of the two extremes. And that is where I guess your training as a particle scientist comes in, so that you get the minimum amount of information needed and simultaneously the maximum amount of information needed as well. You do not want to exceed either limit. The fourth class of shape analysis techniques that I mentioned was simple verbal descriptors. See, when we have defined these shape coefficients, whether it is flatness or whether it is roundness or sphericity or rugosity, whatever, instead of simply representing it by a number, if you can associate a word with it, again it becomes conceptually and intuitively easier for people to understand. For example, if you have a particle that has a very high elongation ratio, so L by B is a very large value, instead of saying L by B is a large value, if you can say that the particle is needle like or fiber like, it conveys so much more, right, as an image, as a visual characteristic. So this fourth group of shape classification methods simply associates various verbal descriptions to the shape coefficients that we have derived in the other methods. For example, you could call a particle rod like, if it essentially has cylindrical features. You could call it fiber like, you can call it needle like, you can call it spherical certainly, you can call it elliptical, or you can also call it something that is a little more descriptive. You can say that it's particularly if the particle shape itself has certain non-uniform features, you could say that it's a combination of rod like and sphere like features. So the ability to express shape in terms of words certainly brings a lot more clarity to what you're trying to convey. And in fact, there is something called a particle atlas that has been published. I think a copy is actually available in our library. So if you look it up, it will actually tell you the various verbal descriptors that people have come up with over the years. There are literally hundreds of them that people have essentially done shape analysis and represented the shape that they are seeing by words. Now the reason that verbal descriptors are important is because they do give again an ability of various labs to collaborate, but it also increasingly highlights the importance of having convergence in descriptions between these labs. Two labs cannot look at the same particle and one says it's a needle like particle and the other says it's a rod like particle. So this particle atlas actually gives fairly precise definitions of what each of these verbal descriptors mean, but typically it's not done in a quantitative fashion. Instead, the particle atlas, just like the name suggests, instead of providing maps of continents and nations, it actually provides images of particles. So for a rod like particle, it will give you about 10 images of what a rod like particle is, so that you have a good, again, intuitive grasp of what people mean when they say that it's a rod like particle. So essentially it gives you a spectrum of figures, diagrams, photos that you can look at and then compare your particle against each of these and say that this looks most like this, so I'm going to call it a rod like particle or a needle like particle or whatever. So that's again the verbal method is actually used as a supplement to the first three methods we discussed. Whether you are doing single particle analysis or bulk powder analysis or mathematical analysis, ultimately you have to communicate to other people what you think the shape of the particle is. They are not going to be happy just getting some numbers from you. That is why even if you are trained in the other three methods, you still have to know how to express your results in a way that makes sense to other people, and that's where the verbal descriptors come into play. All right, so we'll stop at this point, and in the next class we'll start talking about some methods, statistical methods for pattern recognition, which is very important in shape assessment. Any questions? Okay, see you at the next lecture.